So it's my pleasure to welcome Yannis Smaragdakis from the University of Athens. Yannis is a full professor there, and before he was a professor at the University of Massachusetts at Amherst. So Yannis is very well known in the area of programming languages, program analysis, software engineering. He's done a lot of important and fundamental work in this area, and specifically in the area of declarative program analysis, DataLog-based analysis. His work is the recipient of many awards, and I find it very, very interesting and important. So please, go ahead.
Well, thank you, Martin, for the excellent introduction. So this is going to be a talk about declarative static analysis and zombies. And I think you probably understand the reference if you've seen this series of nice books that combines classics together with something big and scary, like Pride and Prejudice and Zombies, and I don't even remember, the Sea Monsters, Sense and Sensibility and Sea Monsters or something like that. But really the point is, I'm going to combine two different topics. One is an overarching topic of declarative static analysis, and then I'm going to go and talk about something scary, which is actually very recent work. It's a paper from this past summer that has to do with a truly sound static analysis, which is something very hard, as I'm going to explain if you're not already familiar with that. So everything I'm going to present is a project that has been running for about 10 years now. So multiple collaborators, you see many names. Two of them are in the room, like Konstantinos and Nikos are now in Switzerland, so they're in the room somewhere, although I can't see them right now. So lots of people who should get credit for this. So what do? We do static program analysis, which you probably know means we try to discover program properties that hold for all executions, not for a single execution under some specific inputs. And the vision of what I'm going to try to present, the declarative static analysis approach, is that we would like to create an intelligent system that in the end will end up knowing much more about your program than you do. And we will see how we're going to go about this vision, but the main approach that we're going to promote is what you've also heard in other talks before, which is a declarative approach. We're going to have a logic-based specification for all the analysis reasoning. So we're not going to write imperative algorithms, we're going to write declarative logic clauses, and collectively, many hundreds of those will give us exactly the result we want. And I'm going to explain that the frameworks we currently have are fast and powerful and have yielded many algorithms that are completely independent of the declarative approach. They are algorithms that you can implement in any other way you want. Now, please stop me throughout the talk to ask questions. I expect, especially the second part of the talk, you may have questions, but feel free to stop me at any point and let me worry about the recording. I may have to repeat your question, but it's my responsibility. Okay, so concretely, the big framework that we've worked on, the big library, the big tool we have produced is Doop. It's work that's been going on for 10 years. It's a framework for analyzing Java bytecode, and I'm going to emphasize Doop in this talk. It's building on pointer analysis, but think of it as generally any value flow analysis in Java bytecode. So at any point in the program, what's the value I should expect? What's a superset of the values I should expect? So Doop is declarative, obviously, and has had lots of offshoots. So we have a framework for LLVM bitcode, and now we're working on Ethereum smart contracts, so we do static analysis on those. And I'm not going to talk about this work, but we will hear from Sokyung in the next talk about vulnerabilities in Ethereum smart contracts, so that should be interesting. But I would like to go on a tangent for 1 second, for 1 minute, and just say, in this work, I can claim we analyzed 38 million lines of code in 8 hours. So every time you hear very large numbers about lines of code, I mean, you should always ask, what's really the depth of the analysis? I can analyze as many lines of code as you want, in as little time as you want, as long as I don't model any central data structure. If I don't model the heap, if I just pass parameters around through functions, I can get impressive numbers. So yeah, sure, we can get 60 threads running on a single machine, pretty large memory machine, but still a single machine. And in 8 hours, we analyzed the entire Ethereum blockchain, which is 140,000 different contracts right now, 140,000 different programs that give rise to over 6 million contracts right now, to be exact. But overall, close to 40 million lines of code. But that doesn't mean anything. So the warning is, every time you hear big numbers about an analysis, ask really, what's the essence of the analysis? What's the precision that you get? So Doop is based on pointer analysis algorithms, and pointer analysis is a big, complex domain. And you may have seen terminology of this nature. You may have heard of flow-sensitive algorithms and field-sensitive algorithms and heap cloning, context sensitivity, implementation techniques, binary decision diagrams, all of those complex things, which I bet if I ask, there's probably not a single person in here, including myself, who can define every single one of those. And these are the kinds of things that you find in research papers, and there are thousands of research papers, if you look right now in the ACM Digital Library, that talk about pointer analysis. And what do these algorithms look like typically? Well, here's a figure. Here are figures from a single paper that we read around the time we were starting the Doop project. So here's an algorithm. That's figure 1. Don't try to parse it. It's not going to be possible because here's figure 2, and there's more. Figure 3, and figure 4, and figure 5. And now I need to shrink the font because figure 6 is even longer, and figure 7. And you get the idea. If that's a single research paper, if you describe the algorithms imperatively, how can we get any confidence that this is correct? How can we get any sense of what's going to happen, how I vary the precision and the scalability of the algorithm if I change a single aspect of the implementation, maybe the low-level data structures, or if I change a single aspect of the design, maybe I have deeper context, for instance. And that's exactly what we try to do with a declarative framework. We try to have a framework where the specifications are not nearly that complex. They're highly configurable, so we have clear variation points. Every time we change one of the parameters, we know that we're getting a different algorithm, but we know which direction we're going to. Do we want more scalability, or do we want more precision, or what? And maybe it's easier to reason about correctness, even informally, because it's still too big to do anything formal. We will talk about many tens of thousands of lines of code. And we can kind of compare intuitively precision. Now, what I'd like to emphasize before we go into the declarativeness is that program analysis is a domain of mutual recursion. Anything you try to analyze is going to be mutually recursive with various small algorithms in related but kind of different domains. You're trying to compute points to information or value information for local variables. Well, you definitely want an image of the heap, like what happens for field points to. You definitely want some modeling of exceptions in a language that has exceptions. And that there are actually, published algorithms that focus entirely on this, how to match throw and catch clauses in Java programs. You definitely want an analysis for the call graph. I mean, points to information depends on the call graph, because obviously you pass arguments into, pass values into arguments and you get them back. But vice versa, the call graph depends on points to information, and so on. Any interesting feature of the language you think of, you may have specific rules for modeling it. You may have some logic for modeling it well, and it may require significant algorithmic innovation to just do, for instance, a good modeling of reflection. But that's going to recurse. That's going to need to appeal to the implementation of your base points to analysis, and the implementation of your base points to analysis will need some information from reflection. So the way I'd like to present this is as holistic program analysis. Everything is connected. If you've seen Dirk Gently, he's a fictional detective by Douglas Adams, the author of Hitchhiker's Guide to the Galaxy. It's also a TV series now, which in Europe, it's on Netflix. In the US, it's on BBC America. Highly recommended. Season 2 is out. The slogan is, everything is connected in a mystery. And it's the same in program analysis. So we have holistic program analysis. And we try now to tackle all this complexity, all these mutually recursive subdomains, and to integrate all those little sub-algorithms into a coherent whole. And I think this is a vision that goes towards this intelligent system that will know more about your program than you do. So we want to encode all analysis aspects separately, but have them interact with each other. And I'll try to illustrate how this happens in the Doop framework. Now, the technical key behind this is obviously the declarative approach. So we will have a declarative specification for all sub-algorithms, but they will monotonically build more and more results. So in Doop, we use DataLog as our implementation language, which is a very simple language. It's really relations, logical relations and recursion. So most computation is either relational joins, just like we know from databases, or recursion. Think of it as the parallel part and the sequential part. That's how complexity theory theorists think of it. There's a parallel part, there are joins, you can do them massively parallel, but every time you need to sequentialize, you use recursion. And you can do all sorts of computations like that. So DataLog is declarative. So unlike Prolog, anything you see in a logical rule can commute. So you can evaluate the body of a rule in any order, the clauses in the body, and will give you the same result. You can examine all rules in any order you want, and will give you the same result. That's what declarative means. So it's more like logic and less like writing an actual algorithm. Plain DataLog captures the p-time complexity class, which means every DataLog program is polynomial time. Every polynomial time algorithm can be expressed in DataLog. That's not too interesting, obviously, because in practical implementations, we first go beyond that. We have Turing-complete programs in DataLog. There are extensions to do that. And secondly, because just if you say any polynomial algorithm is expressible in DataLog, sure. But if it's a linear time algorithm, if you write it imperatively and becomes quadratic when you write in DataLog, that's not really expressible. So it's theoretically expressible, but sometimes not. But the point is, it's a logic-based language that turns out to be very convenient in our setting. So I know about half of you have seen DataLog for program analysis. Can I see a show of hands so I know how fast or slow I should go? About half, I would say, right. So, and half of you have not. So quick introduction, how do we do declarative program analysis? First, we represent the program as a database. So start from a program, very simple here. In actuality, we probably do it in a normalized language, like intermediate representation, like Java bytecode or some 3-address code, and represent everything as a database. So we have tables, and here we maybe the relevant tables are just two tables, alloc for all allocations of new objects, and move, which is compiler lingo for take a variable, take a local temporary, and assign it to another temporary. And you can see that the tables mirror exactly our program, and in reality, we have hundreds of different tables that get produced for a Java program in our framework. And then we have the program. And again, oversimplified, that's the hello world example in DataLog that kind of demonstrates the language without adding too much complexity. It's not really an interesting computation. It's actually a trivial computation because it's just a simple transitive closure. But think of the rules. First of all, let's look at them syntactically. I have two rules here. And the rules have a head, and they have head relations, and everything is relational. And they have bodies. So heads and bodies are separated by this arrow symbol, or you can think of it as a Prolog-style arrow, the colon dash. And we have body relations, just like we had head relations. And here, I say, this here is a join variable. So one way to think of DataLog evaluation is that this is just joining tables. Here, down here, I say, join this table, move to, from, with this table, var points to from obj, so from needs to be the same, that's our join variable, and the result of this join just goes into var points to. So you can think of it in terms of relational joins if you want to, or you can think of it completely intuitively, especially with these simple examples. Namely, you can say, what does this mean? It means we have a base case here that all the contents of the alloc table become var points to contents. So if an object is allocated initially into a variable, that variable points to that object, which is intuitive. And down here you have if a variable from points to an object, and I have a move from variable from to variable to, then obviously variable to points to that same object. So the rules are completely intuitive, and we do have recursion here, as you can see, but this is linear recursion or just transitive closure. But as you can imagine, we keep doing joins. The first result is just a copy, it doesn't even have a join, and then we start doing joins of this relation with the original one based on the second rule. So I'm joining, for instance, this tuple with this tuple, and I'm producing a new line here, a new tuple here. You're following everything, right? Simple enough? So we just join this with that, produce this. You can think of it in terms of joins, or you can think of it in terms of logical inferences. And we keep doing this up to fixed point, when the contents of var points to can no longer change. So that's the high-level idea of declarative analysis. So Doop takes this and makes it realistic. So it has a very rich set of analysis. It uses many of the buzzwords and actually makes many of them parameterizable. And it also models a lot of the Java features. So in terms of static analysis for Java bytecode, it's probably the most complete framework out there right now. It models lots of semantic corners of the language. It has a pretty full modeling of reflection, but also lots of other weird things that every single one of those, if you want to scale to realistic programs, you need to do something about. Now, there have been past approaches that have done things declaratively, because obviously the way we learn static analysis, even in compilers, is declaratively through data flow frameworks, for instance. We learn transfer equations, so we know about the declarative approach. So that's not too surprising, but at the same time, before Doop, declarativeness had been considered largely unscalable, both in complexity, to just write all this hugely complex specification, and in performance. So for instance, here's one quote by Meyer Nike, who has written the J-Chord framework over BDD-BDDB, which is another declarative engine that has done static analysis declaratively, which basically says, well, I do this for prototyping, but then we really write the analysis in Java. That's not what we do. All the heavy lifting is done in DataLog in our work. So it's a lot of DataLog, let me tell you that. Not just for Doop, but also for every other framework we have. Similar complexity numbers apply for the framework for LLVM bitcode or for Ethereum VM bytecode. Maybe not as large as Doop, but almost. So the core specification by itself has over 1,000 rules, like 1,500 rules. We'll talk about 30,000 lines of code in logical specification. So there are many, many rules that all come together to conspire to compute what your program can really do in every possible scenario. And we try to leverage efficient DataLog engines and get as much of them as possible. And we came up with a couple of techniques and got pretty good performance improvement. So I'm not going to talk too much about that, but I'd be happy afterwards to talk individually if anyone is interested. So this was kind of unexpected, and a couple of quotes from back 10 years ago, again, when we started this. People didn't think, first of all, that it's even possible to write, to express all that semantic complexity of a language in declarative rules. So that's a quote from Andrei Lotak's PhD dissertation. And then people didn't think that this would even scale with the very simple implementation techniques we are using. We're using B-trees and tries underneath in our DataLog engine. No BDDs, nothing very fancy that does ideal compression or anything like that. And yet it scales great. And very quickly, to give you an idea of how well it scales, that's a graph from, again, 9 years ago. That's the first comparison of Doop with a paddle framework. And for identical results, so we're talking about identical output, Doop was about 10 times faster. For fairly complex algorithms, it could also scale to more complex algorithms than paddle. Much of this was due to the power that we were getting automatically from the DataLog engine of incrementalizing the computation. If we had to do this by hand, it's not so easy. We humans are really bad about taking something and incrementalizing it. And imperative algorithms, when you try to incrementalize them, are not so easy to do. So we try to avoid them. And if you have written by hand a data flow engine, any data flow overstatement, you know very well what I'm doing, because what I'm saying, because every time you do it, you will skimp on the incrementalization every time. So that's the quick idea. This was very surprising to us as well. Back in 2009, we would have been happy to be twice as slow as a good framework, not 10 times as fast. So it was surprising. Yes?
What exactly do you mean by incrementalization?
So what exactly do I mean by incrementalization? So many of those inferences, on the next step, you only need to apply them to the new results from the previous step. Like when you have data flow through a back edge, you only need to apply it to new facts that came from the last step. That's not so easy to write programmatically. I mean, we can always do it, we know, but it's a lot of complexity and humans don't want to deal with that complexity. So I think I'm done with the overview part of the talk, so I will just do very quickly a couple of things. Doop has led to tons of algorithms that were discovered just using the declarative approach without actually needing the declarative approach. So we have lots of papers that have proposed scalable new algorithms, especially for different variations of context sensitivity. And then there are many, many work threads, many more things that we have done. Instead of a standard analysis, the May .2 analysis, we have must alias analysis. We have lots of work on soundness, and I'm going to talk about that. We have optimization techniques. We have algorithms for how to deal pretty well with a parcel program when we're missing parts of the libraries, et cetera, et cetera. So all of those have led to many different publications. So it's been a very fruitful area for us throughout the past 10 years. So now that I'm done with the big overview, let's face our zombies. Let's face soundness. Who has seen the concept of soundness in static analysis before? Most everyone, okay, or at least 70% of the people. It's something we all want, right? It's a good thing that we can all agree on. Soundness is great. What does it mean? So soundness means that whenever the analysis makes a claim of a property P, that implies that P truly holds. Which seems pretty simple. Man, the analysis should only make true claims, right? If I claim P, P truly holds. Let me narrow it down just in the context of the talk. Although this is a general definition, let me narrow it down so you have a mental model of what I'm going to be describing so you can see when I'm presenting examples in the next few slides what I mean. Imagine that we have a May analysis for value flow. What does May mean? May means the analysis is over-approximate. It tries to compute a superset of what happens in practice. So what does value flow mean? Take any program variable or any program expression and give me a superset of all its values, all its possible values. Right? Do we have a mental model? Static analysis goes over my program and gives me a superset of the values for every program point. Right? Okay. So soundness is kind of a design property of an analysis. So people who have designed static analysis, they often talk in these terms. They use vocabulary like this. Does your paper handle arrays soundly? So it's a design property. Okay. Now, the first claim from the Soundness Manifesto, which was kind of a viewpoint article in the Communications of the ACM a couple of years ago, is that there's no practical, static, whole program May analysis that is sound. Whatever you thought of before, when you thought of an analysis that gives me superset of all practical values at any point in the program, it can never be done soundly. It has not been done soundly so far, is the point. Is anyone surprised by this? No one. Okay, That's good. So the soundness manifested, which got lots of objections, seems intuitive. So by whole program here, we mean an analysis that does model global effects. It models the heap. Obviously, I can give you sound results if I just say every program variable points to anything or has any value, right? If I make all value sets be top, I can give you a sound answer, but you will never find an implemented analysis algorithm that does this because it's useless. So no useful algorithm is actually sound, is the point. No implemented one that's in actual use is practically sound. But there are all these soundness proofs. So where's the difficulty? Where are the zombies? Where are the dragons here? So the dragons are in that the proof is for a limited language, a specification that we state in a paper, and that proof cannot be extended for the full language. There are many technical difficulties, and it's not the proof that cannot get extended. And that was my point when I said soundness is a design decision. It's not the proof's problem. It's not that the proof is hard. It doesn't hold. The analysis itself is never sound because of dynamic features in every realistic programming language. And in Java, for instance, we have reflection, dynamic loading. We may have eval in other languages like JavaScript or Python, Ruby, whatever. For instance, if I have with Java reflection something like this, that gets a method name and dynamically looks up a method using reflection and a class over that object and invokes that method on that object, most static analysis frameworks will not resolve this correctly because meth name could be a complete runtime value. What are they going to do? Are they going to say here at this point, I may call every method? In practice, they don't. Yes?
There are realistic languages that don't have reflection, dynamic loading, or eval. Are they part of static?
Which are those? Name one.
ML.
No, it has more dynamic features than those. It has native code for one thing. Most of anything you do has native code that accesses shared memory. There's no realistic language that can completely avoid this. You cannot have static analysis unless you go into the native code, which will do exactly those things. It will do exactly those low-level things. So yes, you're right, the language itself, fine, but your programs will go into a library and the library will use native code, which is opaque to your analysis, and it's definitely going to be using tricky features. So in practice, this applies to all realistic languages in analysis. There's unsoundness, and somewhere we need to wrap it. So what I'm going to talk about from this point on is a new algorithm. It's a truly sound analysis. Of course, it has lots of shortcomings. It has lots of restrictions, and we will talk about those next. But the point is that it does solve this problem. It's actually fully sound for a realistic language, and there are three novel elements here. It's a different form of a soundness theorem, so that's the first thing, and I think you will get this, and I want you to get this regardless of your background. You will see that what I'm trying to prove as a soundness theorem is slightly different. It's going to have a defensive design that will withstand all this weird code. So it will be able to resist opaque code. And if you've done a bit of analysis, you may appreciate this. And then we'll talk about the requirements for the implementation, because those are also pretty heavy. So let's talk about the first part. Different form of a soundness theorem. So this is the conventional soundness theorem. This exact formulation is by Xavier Rival, but it's of broad use in the abstract interpretation community. The soundness theorem says, and that's kind of a template of what you will see in actual papers. It says, for all programs in the stated language subset, in a given language subset, and all executions in a stated execution subset, and the exact theorem will define what subset in both cases, we have soundness. If the analysis claims P, that implies P, which means that soundness is always qualified a priori. So a priori, I have restrictions on my program and on the dynamic executions for which my theorem holds. And the problem is exactly that these qualifications don't hold in practice. Even if you have the best abstract interpretation framework with careful proofs of soundness, you have Astray. It works for C, but doesn't work for C with dynamic allocation. It doesn't work for C with malloc, for instance. And realistic programs, well, you've written C, After your first year, you use malloc. There's nothing realistic written in C that doesn't use malloc, except in some industries that use C to express control systems. And why one uses C to express control systems other than because there was no other language back when the control system was written? I don't know. So you get the point. This is highly qualified all the time, and the qualifications preclude realistic programs. So it's even worse. I will editorialize a bit and say that the problem is that this form of the soundness theorem creates perverse incentives, because it means that the weaker my analysis, I will just focus that my analysis doesn't handle arrays soundly. Well, fine. In my paper, I'm not going to put arrays in at all. They're not going to be part of my input language in the paper. I will just specify, I will just give an input language without arrays. Well, great. So typical proofs start from formulating the analysis over an artificial input language, and this means that the weaker your analysis, the more likely you are to omit features from that input language, and the easier it is to prove your soundness theorem. So many times in practice what we see is that you have a very unsound analysis, well, that makes you focus on the right subset of the language, so you have an easier soundness proof. Theorems have to be examined carefully with respect to their qualifications. So the different form of the soundness theorem in this work is the following. We don't a priori qualify the language subset or the execution subset. Instead, what we say is, for all program points P in stated subset, and that's not stated by the theorem, that's computed by the analysis, the analysis claim at the program point P implies that it's true. In other words, the analysis works everywhere, for the entire language, for the entire program, but it only gives you results for a subset of the program. It gives you certified results for specific program points. It says here, check mark. I can certify that this answer is sound here. So go back to our mental model. We have a value analysis. We want a superset of all the possible values at different program points. The analysis computes sets, and then it certifies when these are guaranteed to be supersets of the actual values that will ever arise. And many times it will not be able to certify it. So many times the analysis will say, well, I cannot give you a superset here. There are dynamic features that could affect this part of the program. So this introduces, yes?
Is that a reasonable size?
So we'll see that in the experimental results. So let's go forward a bit and answer that for a points-to analysis for Java, I can give you sound results for about 40% of the program. So it's not half the program yet, but it's not a trivial subset. So I can give you guaranteed results no matter what you do, no matter what other code you load, no matter what your native code does. It can be completely hostile native code, and still I can certify about 40% of that program as being sound. So this introduces the concept of coverage. You'll hear me use the term, which is how big is the subset of the program for which the analysis certifies soundness. Does this make sense? Okay. Okay, so the second thing, that's kind of the technical part, which I will try to illustrate with examples. It may not be too surprising. Some parts will surprise you a little if you designed algorithms, but it's not too surprising. So we have a defensive design that can resist to opaque code. So we already formed this mental model. We want all the possible values that may ever arise at runtime. How can we be sure that we have all of them? Well, we first need to closely track information all the way from the source and ensure that there's no possible interference between the source of a value and where we are actually examining whether a variable holds that value. So we need a very, very precise analysis to keep track of this information very precisely. So we need a context-sensitive analysis, flow-sensitive, and you will see what I mean by over-access paths. Yes?
If you include native code as being a potential source of things that you don't analyze soundly, as in response to Suresh's question, then how can you ever rule out any program point as being potentially unsound?
Okay. Because we assume a well-typed language, so we assume that native code, whatever it does, can never affect my stack. It can only affect my heap if a pointer to the heap, to that particular part of the heap, has escaped into native code. So if you're saying, well, but native code can go and mess my entire stack and heap, sure, but that's very low-level native code. If you're thinking of native code that still respects the well-typedness of the language, those are part of the assumptions that I have not stated in the presentation that are in the paper. That what do we assume? A certain model for threading, a certain model that our outside code cannot go and mess with my stack. My stack is private, so to speak, and it can only mess with my heap if something has escaped. Yes, right.
So what about a garbage collector? That can be triggered at any particular point in the execution.
Again, if the garbage collector, when it does the stack walking, it can mess my stack, then that's no guarantee holds. There's no way to have any guarantee that...
It walks over the entire heap, presumably. So
No, that's perfectly fine. That's perfectly fine because that's transparent. If you assume that the garbage collector is correct, we're good. I mean, when you do a static analysis of a program, you're not really trying to prove that's going to do well under any garbage collector that may corrupt your heap. So I'm saying we're doing a static analysis of the client program, of the application program. Yes, we can assume that the garbage collector is not going to mess up my heap.
So there's a trusted, I guess my confusion is that it seems like there's a notion of a trusted code base here, because initially you were saying native code can do all sorts of things that you don't understand, and that's the reason why you can't make
But I am
decisions.
calling that native code. I'm not calling the garbage collector. So I can assume that the garbage collector is correct. That's part of the runtime environment. The native code that I'm calling, when, for instance, I pass a pointer to the heap into a library, that can do anything. If I do native calls, invoke dynamic, whatever, I'm calling that, though. Walter.
Yeah. How about the data races on 64-bit entities that are not guaranteed to be assigned atomically?
I missed the last part. Data races
on values that are 64-bit, and the GVM doesn't guarantee atomic assignment on them.
So I don't think we have any values that we keep track of that are 64-bit anyway. But for data races, I think the realistic thing is to just assume a very simple thread model. We have not looked into anything low level in terms of atomic operations. So most of the results I will show you are either assuming sequential, like no thread interruption, or they're assuming monitor style. So monitor style means you definitely have monitor enter, monitor exit whenever you access shared memory. So there are these assumptions, there are background assumptions, but still, under those which are realistic, we can analyze programs soundly. So insight technically or intuition technically, obviously, at this line here, you know what A points to. We are sound, right? There's no question about that. We just got a direct assignment of a new object to A. So here I can give you a sound points to set. That's what I meant in the previous slide when I said we track information from origin. Same down here. Now, both of these new objects, they get passed as arguments to the ID function. So what can I say soundly about this A here? That's a question for you. What's a sound value set for this A in ID? Why top?
Because you might not know all the code.
Aha, that's excellent. So a conventional analysis would typically say a sound answer here is A1 and A2. That's not the case. I don't know all the code. I don't know who else is calling ID. That's not a sound answer. The sound answer is either top, which makes our analysis useless, or it needs to employ more precision through standard context sensitivity. So the real sound answer for our algorithm is that A here points to new A1 under the assumption that the caller is foo, and points to new A2 under the assumption that the caller is bar. Standard call site sensitivity. Certainly, I cannot drop these contexts. In typical unsound May analysis, I can drop the context whenever I want. They are just there for precision. Here, contexts are necessary for soundness. Whenever I don't have enough context, I have to revert to top. I have to always say top if I don't have enough context to keep the information back from where it came from. So, and of course, if I have this precision, then I know that this B also points to this, and this B also points to that, and you already got an idea of the first few of the formal rules defining this algorithm. Yes?
I thought we were talking about whole program analyses.
It is whole program, yes.
And
So the next slide is going to show heap operations.
so do we mean by whole program that you have access to the entire source code of the program? Or is it
No, no. I'm giving sound points to sets modularly for the parts I do have access to, and there are other parts. There's dynamically created code that I will never see. There's native code that I will never be able to analyze. So it's what I can certify without making any assumptions about that extra code, minus the standard threading, etc. stuff.
Is it analysis that holds true with respect to an arbitrary context?
Yes, yes. I could even analyze this function bar without looking at any of the rest of the program. The problem is that in that case, other than this line, I would get top here. So you can always analyze as small a part of the program as you want. The problem will then be that your coverage drops significantly. So the more of the program you have, the more coverage you get.
I guess, Yannis, this is like a necessary precondition. The foo and bar color is like a necessary.
Yes, this is a necessary precondition. So contexts in this analysis are used as necessary preconditions. Okay, so you already got trained to think defensively. What do we know after this statement? I have an assignment of a new object to a complex field. Obviously, in a typical intermediate language, those would be two statements, but that's still fine. So I know that program expression x.fld refers to A1, to this new object here, right? But that's the other interesting part of the analysis. I know this regardless of what x points to. As long as I get to the execution point after this line, as long as x is not null, in other words, regardless of what x refers to, I know that x.fld refers to A1, right? And this is the second design aspect of the analysis, that this needs to be an analysis over access paths, over program expressions, not an analysis over abstract objects or anything less precise. So to be sound, access paths are fairly essential. Also in this case, if you want to be careful, really it means because you cannot rule out aliasing between x and any other access path that you know soundly at this program point. It means that any other set that ends with .fld that you have a sound knowledge of before this instruction now needs to be augmented with A1 after this instruction. If you got this, you got the essence of the analysis, because it's not that much more. It's access paths kept track of very precisely throughout the program code, and certifying what code is absolutely analyzable with no interference from reflection, dynamic loading, possible dynamic loading, native code, etc. So, to emphasize a point, whenever the analysis is uncertain, it has to revert to top. It has to refuse to certify the soundness of a points to set. For instance, let's say I have this here, I have two branches. And on one branch, I know the points to set, I know the value set of this access path, x.fld. Right? x.fld points to A1, and I know this soundly, for sure. Do I know anything after the end of the if? And the answer, as the slide says, is no. If I cannot analyze this code, this foo code, maybe because it's too complex a function, and to analyze it fully up to the very last instruction reachable, it will require much more of a context depth than I have, or because internally this uses reflection, or internally it may call dynamic native code or whatever. If for whatever reason this foo is opaque, I don't know anything about the value of x.fld after the end of the if. I mean, even though in one branch I know what it points to. Okay? Okay, so I think we're done with a really hard part here. Yes?
If you assume like asynchronous code and you assume you have a reflection or some other presence of some other dynamic features, then you can't even guarantee anything, even just after this new A object statement, right? It can be.
I can guarantee things here. I can guarantee that right after this statement, this is the value of this expression.
Do you assume
the only thing that could violate this is multi-threading when X has leaked to a different thread, has escaped to a different thread.
Right.
But let's stay sequential for now. Let's just say there are no threads, just for simplicity in the exposition. And 80% of the paper, actually, if you go through it, it will assume sequential, and then it adds this escaping notion.
Okay.
Okay. Now, just for reference, in order to implement this realistically, it also needs an implementation trick. And the implementation trick is the following. We don't even compute point-to sets unless we can also certify their soundness. In other words, we use the empty set to mean top. And every time we have a non-empty set, it means it's guaranteed over-approximate. It's guaranteed to be a superset of the actual values. If I cannot give a proof that this is bounded, then I don't even compute it. So I will skip that, but that's an idea that I wanted to get through, but I'm out of time with all the questions. So really, to give you an idea of how good this is, it's not a trivial analysis, but it scales about as well as a precise unsound analysis, like a two-object sensitive analysis in this graph. And for realistic programs, these are really the lines you should look at. This red line here is the mean across many benchmark programs for the most defensive setting you can have. And this means under all contexts, no matter who may call you, that's how much of the program I can prove soundly, I can have points-to sets soundly, that red line. And actually, the blue line is a little more realistic, but it's a technicality, and I don't want to get into that. But let's say 36% of the program under the most pessimistic thing you can imagine, I can actually compute sound value sets for. This black line for reference at the bottom is what an intra-procedural analysis would do, what a standard compiler or VM would do. So we are significantly better than that by going interprocedurally with precise context.
So this is percents of points to sets.
That's percent of program variables in SSA form, so they really correspond to program points, because we've done the SSA transformation, that have sound points to sets. So real client, devirtualization, I can devirtualize 37% of all virtual calls, and I can be sure that this is a correct transformation. So this is really everything I had. I gave an overview of my research the past 10 years. So I think of Doop as an early instance of an intelligent system that just knows things about your program. And I also gave you a glimpse of some recent work of just this past summer, presented a couple of months ago, the fully sound analysis, which is kind of surprising that this thing even exists, despite its limitations. It's a fully sound analysis for realistic languages. And such a thing is possible, but has a different form from typical program analysis that we have. And the insights, we just discussed them, different form of a soundness theorem with coverage as its key concept. Thank you very much.
We have time for a couple of questions, but Jan, well, go ahead. Yeah.
How do you state and prove the soundness theorem for Java?
How do I state and prove the soundness theorem for Java? So that's a good question, because I cannot do the typical thing of giving a dynamic semantics and abstract semantics and trying to connect the two formally. So the proof is informal. The proof has to be informal, because the statements that I just gave you, that, for instance, native code cannot go and crawl my stack and change things, this is also an informal statement. So the proof goes over all the different cases, and it says, under our three, I think, assumptions, informal assumptions about what unknown code could possibly do, here's why, after this instruction, the rule guarantees to give an over-approximation. Because nobody can crawl my stack, this is a direct assignment to a local stack variable, so blah, blah, blah. So it's an informal proof, but it's very systematic that goes over the syntactic elements. Again, this is an analysis that only reasons about what it can see, does not reason about what it cannot see. It's defensive relative to anything it cannot see.
Is a good way to think of it. I'm inferring the preconditions. So for this points to set that I infer the preconditions, then I'm sound there under these preconditions, right? And for the other points to set, I may have some preconditions, but I may be sound or I may not be sound there.
If I may not be sound, I don't even compute the points to set.
You don't even compute it. So basically, any points to set you compute, it's sound.
Points to set I compute. I have found all the paths where values can flow to it, and I have certified every single one.
Well, I'm saying these preconditions are just expressed over paths, but it could be expressed over some numerical thing or whatever.
Right. It's a flow-sensitive analysis with context sensitivity. So it expresses preconditions as this specific instruction, no matter how it got from the top of the function, and it goes up to 5 or 6 context sensitive. Right. Who are the 5 callers back to the stack? And if that's enough to prove a points to set sound, then it proves it. Otherwise, it just says top.
Mm-hmm. Okay. Yeah, last one.
So you're saying that this is a flow-sensitive analysis, so you do consider destructive updates?
Yes. To the heap, right. to access paths right. on the heap, yes, we do. But it has given us nothing. It has given us like 1% more coverage, really.
Right.
It's very rare that we can prove enough.
Is there any problem with weak reference? How do you deal with weak reference?
I don't see why that would be
weak reference because you can lose that reference to garbage collector, but you don't see any update in the program. The garbage collector determines, right, whether or not this reference is taken.
But we only do an update over actual objects that we have names for, so they will never be garbage collected. It's not that something can ever be.
No, you can create a weak reference object, right?
Right.
And then the weak object reference, the object would basically tell the garbage collector that it's up to the GC whether or not this reference is taken.
But I think that what will happen in our case will be we will never get to the next statement because the reference will be null. So we say x.fld, and you're saying x may be a weak reference. Right. You may think you have a value there. Let's say it's a weak reference. Let's say it can be garbage collected, which I don't know if that's the case. I know weak references, but I don't think, because every time we know that the object actually has a name in the program. But even if x becomes null, we will never get to the next line. We will have an exception. So our guarantee, the guarantee of the algorithm is always, if you get to that program point, that's the superset of the possible values of that program expression.
Okay, good. So let's thank Yannis again.